we already have that a of t is 6t minus 18. That's the acceleration. A of t equals 0, I meant to write 0, means 6t minus 18 equals 0 or t equals 3 seconds. That's when basically the velocity has a, right, the tangent to the graph of the velocity is 0. So t equals 3 seconds. Now you will see why I added the acceleration here. It is 0 at 3, and I need to study the sign of the acceleration. So this is the acceleration. Please plug in a number to the left of 3 and a number to the right of 3, and tell me the sign here and the sign here. Remember, if you only remember that, it's so simple. It's a linear function with a positive slope, but only linear. I'm talking about linear, but it's linear with a positive slope. What will be the sign then? Left and right.
Positive.
That's why it's negative.
Yes, it has to be negative and then positive. Don't trust me. Let's plug in a number. Plug in 0. Plug in 0 and see the sign. What is the sign when you plug in 0?
Negative.
Yes. Plug in 10. What is the sign when you plug in 10?
Positive.
Yes. Perfect. Now here's the moment of truth. Remember the two forces. When they work together, the two forces are helping each other. That makes the particle to speed up. When the two forces are working against each other, the particle is slowing down. So I'm going to squeeze in here, conclusion. Between 0 and 2 seconds, is the particle speeding up or slowing down? The velocity is positive, the acceleration is negative.
Slowing down.
Exactly. They are not working together. They are working against each other. Awesome. Okay. Here, the velocity between 2 and 3. The velocity is negative, but so is the acceleration. What does the particle do? In the opposite direction, but we don't care. Is it speeding up or is it slowing down?
It's speeding up.
Yes. Now the velocity between 3 and 4. The velocity is negative and the acceleration is positive. What does the particle do?
Slow down.
Yes, slowing down. Finally, the velocity and the acceleration are both positive. What does the particle do?
Speed up.
Yes. This is a very important analysis to understand what's happening here. So when the forces are against each other, the particle is slowing down. When the forces, regardless of the sign, but they have the same sign, they work together coming back, but that's okay. They are increasing the speed. It's speeding up. Here they're working against each other again, so then the particle is slowing down, and again they go in the same direction. In other words, I ride my bike and there is a tailwind. When I ride my bike and it's a headwind, my actual speed is slower than what I can do. By how much slower? By the speed of the wind. Any questions? Do we understand this concept, these concepts, or this problem? Any questions? Anyone? Anyone? Any questions for me? Okay, well, we do have about 10 minutes left, so I would like to continue just to give you, so till this point, please finish up 3.6 and 3.7 for Monday. The majority of you, thank you again very much for keeping up with the pace. Few of you have fallen behind. I'm hoping that you can catch up. I really hope that you can. Okay, so let's look at 3.10. So the last two sections that we have to cover from chapter 3, 3.9, which is a huge topic, and 3.10 that only has two different situations, two different applications. One of them is something called differentials. And the other one called linear approximation. Also linearization. They go together. I don't know if I can finish either one in 10 minutes. We'll try. But I will start with differentials. So we have some concepts here. We talked about derivative, which we know is f prime of x. We talked about another concept was differentiable. Function. When the function is continuous and no cusp, a corner, or vertical tangent. So the derivative is one thing. A function is differentiable if it is continuous and has no cusp, corner, or tangent. Now there is a new concept. Looks like this, these two, but not really. A differential. So number one is one thing. Number two is something else. Number three is something else. There are two different differentials, dy and dx. What is this? The differential of x. What is this? The differential of y. Not so fast. So let's go back to a graph. We graphed this function many, many, many times. I think I'm going to move to the next page because I want to make it bigger. Sorry about that. And I also want to use a different color. So this is our best friend f of x. Of course, this is our x, and this is our f of x. And of course, this is our second best friend, p, x f of x. And of course, we have our best friend, second, third best friend, whatever, q. Very, very close, but I'm going to zoom in, and now it's right here. And of course, you're going to say, I know what you're going to do. This is getting too repetitive. Okay. So Q and P are very, very close to each other. Very, very close, but I'm zooming in. Yes, of course, I'm going to draw the secant line. You know all this. You've seen it several times already. Yes, I'm going to continue the f of x till here. Yes, I'm going to write that this is, this time, instead of x, this is what we've been doing so far. This time, we're going to change the notation a little bit. We're going to say x plus delta x. So this is delta x. And you can say, stop, stop, stop. You told us this was delta. Now, what is this? This is the uppercase delta. This is the lowercase delta. Okay? So x plus delta x or x plus dx. So this is the same thing with dx. And you can say you're changing the notation on us a little bit. So this is still the little bit, or tiny bit h. But now we're going to denote it, the little h, by delta x or dx, and they are the same. It's this distance between p and x. Very tiny, because q, we know, q is right here. So these are small numbers. Okay, so we have this, which is delta x. This piece represents. So again, we had examples like this. So let me refresh your memory. What is this distance? Tiny, like a little error. So x and p and q should be very, very close, right? H should be 0, or delta x should be 0, dx will be 0. But there is a tiny error. They're not the same. So you can say that this is created by a tiny error, right? This distance is created by delta x or dx, tiny error. But of course, that will trigger a distance or a difference in the y values. So this is the delta y. So a small change in x creates a small change in y. And of course, I'm going to change this into either f of x plus delta x or f of x plus dx. Because we are moving away for a short time, we are moving away from this h. We want now, and you'll see in a moment, why we prefer delta x and not h in this situation. Okay, so let's identify what these mean. So delta x is the actual change. If you want to call it error in x. The dx, which happens to be the same, is the differential of x. What is it? It's, for x is the same, but it's basically obtained for or with the derivative. It's connected to the derivative. That's why it's not the actual change. It has DIFF, something to do with the derivative, the differential, right? So it's obtained or it's connected to the derivative, okay? So this dx is the differential of x. The delta x is the actual change. Yes, they are the same measure, but they have different explanations, if you want, or different meaning. Okay, now, yes, I know you know. I'm going to draw the tangent line here. I'm going to force it a little bit so it's not going out my page. Okay, you'll see in a minute why. So this is the tangent at P. I will extend this line. And now I'm looking at a triangle. So this is the distance delta y. I didn't write it. Let me write delta y. Delta y is f of x plus delta x minus f of x. How come? Yes, it's this, which is f of x plus delta x, minus this. It's this piece. F of x plus delta x minus f of x gives us delta y. And what is delta y? Delta y is the actual, the exact, if you want, the exact change in the function value created, initiated, determined by, created by delta x. It's the exact. Okay, before I lose you, what are we trying to do? This is another application. The differentials are applications of differentiation. And we did not get to the linear approximation. I didn't finish this, but I don't want to lose you in the sense that I just wanted to at least explain. I know I'm almost running out of time. What do I have? I have 2 minutes. I'll stop in 2 minutes, I promise. So we identify delta x. We know what dx is. We know delta y is. And now This is a tangent. And as we did with the problem on the when I printed out and we determined the slope of the tangent, and we also had a problem on the test. How can I determine the slope of this line? Rise over run. Rise over run. So the slope of the tangent at P is rise over run. I know what the run is. The run is dx. But I want to determine the rise between this point and this point. But is there any other way of determining the slope of the tangent line at P? Is there another way that we learned in the last 3 weeks, 4 weeks? What will this equal to? We determine it in examples. We determine it to find. Today we have also had in the discussion, we used it to determine the equation of the tangent line. What is it?
The slope will be y prime.
Exactly. F prime of x. Okay. And now I'm asking you, and I'll stop after you tell me the answer here. If it takes you a day, then we'll stay. No, I'm kidding. So look at the beginning and look at the end and tell me what fits in here, and there is only one answer.
Delta y.
F prime of x, we never used delta y before.
Sorry, never mind.
We never used delta y so far.
F prime of x.
Equals?
Is it dy?
Of course.
Y?
Absolutely. Absolutely. So this is dy. But because q and p are very close to each other, delta y is approximately dy. And dy is the differential of y. We will take it again from here.